Welcome to the I am learning lecture series on atomic and molecular structure. So today I am going to discuss about wave particle duality and the uncertainty principle. In the previous lecture, in the previous video, I have already explained that radiation has two characters, that is wave character as well as particle character. Similarly, in this video, we will understand that particle, even matter, they also have particle character along with wave character. That's where actually the quantum chemistry or quantum mechanics begins, quantum theory begins. So today we will try to understand the beginning of quantum theory by explaining the wave particle duality and the uncertainty principle. So there was a great scientist again in that era whose name was de Broglie. Actually, he first thought that if the radiation can have two character, that is wave character along with particle character, then it might possible that matter can also have the two character along with their particle nature, the wave nature might be possible, because that time de Broglie he was doing his PhD and he actually come up with a completely revolutionary thought that if radiation can have two character, that is wave character and particle character, then the particles can also have two character. At first he first proposed that small particles of matter may display the wave-like properties along with their particle properties. But at that point of time, there was no such instrument which can explain this, so he has to wait for a few years, and he has given a we can say that a beautiful equation which is known as de Broglie equation, which actually connect the wavelength of any matter having mass m and velocity v. So if the matter has mass m and velocity v, then the wavelength associated with this matter will be lambda equals to h by mv. So this equation is very famous and has been utilized later on to develop the quantum theory. So this phenomenon, this proposal that the particles might have the wave-like properties along with its particle character is nothing but known as wave particle duality, or it is sometimes known as dual nature of matter. So now we will try to again understand how it can be derived from Planck's equation. So let's say we know from Planck's equation E equals to h mu, and according to Einstein, because Einstein that time already have given this we can say that very famous equation, E equals to mc square. So if we just compare both h mu and mc square, we can write h mu equals to mc square. Now E equals to, we know that c by lambda. So if you simply type E equals to c by lambda, so ac by lambda equals to mc square. Similarly, if we just do little bit of rearranging, we get lambda equals to h by mc, or lambda equals to h by mv. If instead of c is the speed of light, m is the mass of the particles. If the particle has velocity v instead of c, then it simply will have h by mv, or mv is nothing but momentum of the particles, mass into velocity. So lambda equals to h by 2. So what we can conclude from this, that the wavelength of a moving particle is inversely proportional to its momentum. Lambda inversely proportional to p, its momentum. So now the de Broglie, it was the development, it was the first basis for the development of modern quantum mechanics, which actually leads to the development of electron optics or electronics. So that is the basis for all the electronics you can say that branches that right now is developing, or that right now exist, because the wave properties of electrons have been utilized to design most of the modern electron microscope which we are using day to day life for various activity, like we can say that imaging various viruses for the drug development, for the clinical trial, to understand the properties of materials. Everything has been done by electron microscope, like scanning electron microscope, transmission electron microscope, and various other microscope. And the basis is the quantum mechanics, and again the basis for quantum mechanics was de Broglie hypothesis. That's why you all must know about this wave particle duality. Now there are some proof which is required, because if you say something, people are not going to believe. There must be some concrete or proper proof against each of the proposal, then only it will be recognized worldwide. So one of the proof was that if we hit a beam of electrons to a fluorescent zinc sulfide screen, it produces a spot of light. It is nothing but known as scintillation. So it seems that we are just throwing some particles to the screen. So this clearly proves that electron has particle nature. So this is about particle nature of the electron. So scintillation process or scintillation phenomena proves that electron behaves as a particle. Now de Broglie said that electrons along with this particle, it will have wave nature. So what is the proof of wave nature? So definitely there are some concrete proof for the wave nature of electrons also. And the proof is that Davison and Jarmar in 1927, they were scientists, and they were doing an experiment. What they have done, they actually hit a electron beam which were passed through a small slit, and they hit a nickel crystal, from where it has been seen that the electron beam has been diffracted and it forms a diffraction rings similar to the X-ray diffraction. So X-ray is a wave, and now electrons is also similarly showing the same diffraction ring. That proves that electrons also behave as a wave. So this Davison and Jarmar experiment is a direct proof that electrons are also having wave nature. So now it is completely accepted by the scientists that electrons has a particle nature along with wave nature. So that was very interesting, and it was the fundamental of development of the quantum mechanics. Again, there was another experiment where if you just actually throw a beam of electrons, then if they are particle nature, then definitely the whole screen should be spotted with electron. That means electrons should actually we can say that give spot all over the screen. But it has been seen that actually if we pass through electron in two slits, then throughout the screen there is an interference pattern. That means there are some places where we can say that intensity is high, there are some places intensity is less, but that should not be happen. If it is a particle character, then it must have the same. For example, in this two slit, only two spot we should get, two bright spot, because there are only two slit from where the electron can go. So there should be only two bright spot, and others should not have any bright spot or anything else. Only we should get two spot like this. But in actual experiment, it was found that if we pass through the electrons in this kind of slit, then a interference pattern, that means along with the screen there are alternate, or there are some bright spot, there are some dark spot. So it is a properties of waves, because waves interfere constructively and destructively, and they actually waves moves from one place to another. So that's why moves and they interfere. So it is direct evidence that electrons also have wave character. So particle character as well as wave character. So proof of wave character was this interference as well as the Davison-Jarmar diffraction experiments. These are the wave character of electrons. So now another very much important phenomena that de Broglie has given. De Broglie told that this wave character of the material, it actually can be seen, it can be shown by any material. But if we consider, let's say, electron and a tennis ball, and if we try to compare their wave length, then what will happen? Let's find out. If we just take electron and if we try to find out the wavelength, let's say electron has a mass of 9.1 × 10 to the power minus 31 kg and the speed 10 to the power 6 meter per second. Then if we follow lambda equals to h by mv and we calculate by putting all the values, it gives the wavelength of around 7.28 into 10 to the power minus 10 meter, or we can say it is a close to the wavelength of X-rays, which can be easily measured. We can easily measure this much wavelength. But if we apply the same thing for a tennis ball and if we try to understand its wavelength, let's say tennis ball has 100 gram mass and having the same speed, let us assume, then the lambda becomes 6.63 into 10 to the power minus 39 meter, which is such a absurd value, absurd low value, that no machine in this world right now cannot measure this wavelength. So we can say that the wave character is only prominent for a microscopic or nanoscale materials or very small particles like electrons, but it is not significant for macroscopic materials like tennis ball. Again, one of the important phenomena that leads to the quantum mechanics was uncertainty principle. Now in uncertainty principle, what the scientist has said, that the velocity and the position you cannot precisely measure for a very small particle. That was the actual statement. It is impossible to determine accurately the position and velocity of a microscopic particle at the same time. For a macroscopic particles, for example a tennis ball, a bus, a train, it is possible to determine the velocity and the position accurately. But for an electron, is it possible? No, it is not possible. Because as soon as we try to measure the position, we need to use something. For example, to measure the electron, we need to do some microscopic, or we need to give some laser light. As soon as you put it, it changes its position. So if we wanted to measure accurately the velocity, then position error will be maximum. If we wanted to measure the position, then velocity error will be maximum. So simultaneously it is not possible to measure accurately the position and velocity for microscopic particle. This phenomenon was given by a very famous scientist known as Heisenberg, and that's why it is known as the Heisenberg's uncertainty principle. So what is actual mathematical expression? If delta x is the uncertainty in measuring position and delta p is the uncertainty in measuring the momentum, then delta x into delta p greater than equal to h by 4 pi, where h is a Planck's constant. This is the mathematical expression for uncertainty relation. Or we can write that m for any particle will be constant. So we can write delta x into m delta v. Delta v is the error in measurement of velocity. So delta x into m delta v greater than equal to h by 4 pi, where h is Planck's constant. So this is the uncertainty principle. So if we know the error in position and error in velocity, we can very easily calculate we can say that by following this equation, the mass, or if we know the mass and if we know the error in velocity calculation, we can easily calculate the error in position calculation by following this equation, delta x into the m delta v greater than equal to h by 4 pi. That time we need to take equal to h by 4 pi for solving the mathematical problem. Okay, so now in the next video we will try to understand about Schrodinger equation, or the equation which describes the wave character of electrons, which is the birth of modern quantum theory. Thank you.